Welcome to the lecture series on metal additive manufacturing. In this lecture, we will be trying to cover little bit on basics of laser, because laser is a very powerful tool which is used for joining or melting powder / wire metal powder or metal wire to produce the output. We always can think of using electron beam, but laser has more flexibility and it is economical. Before getting into the lecture, let us have a small recap what was covered in the last few lectures. In the last few lectures, we were trying to cover various processes which are falling under metal additive manufacturing. We saw powder bed fusion method, directed energy deposition method, binder jetting method. These three are very common. Then we saw latest emerging metal additive manufacturing process, metal extrusion, wherein which the metal is mixed with polymer, extruded as a wire and then printed. So, material extrusion, material jetting and sheet lamination method. This material extrusion is quite a common process in polymers, which is called as fuse deposition modeling. So, the same thing is used here. It has better advantages, but this process as on today is becoming expensive because the extrusion, mixing of polymer and metals is a challenge, which we discussed in the last lecture. Today we will try to see systems which are involved in additive manufacturing, laser theory, laser components, what are the two types of laser, continuous laser and pulsed laser, laser types and laser beam properties. We will understand the laser fundamentals in this lecture. When we start using laser, we always have to be very precautious on the safety point of view. Laser, when it tries to hit a metal powder or a reflecting surface, the laser light reflects, and when the reflected light by chance hits your eye, it is disastrous. So, when we are working with lasers, be more precautious than normal machining. Today, do it yourself is a common thing which is available in YouTube. People try to look into that and start developing setups, but when you do that, when you are working with laser, look at the class of the laser and be very cautious to wear laser protective goggles. And laser has a very high energy density. So, be very careful when you are using your free hands also to be very careful. With that small caution, let us get into the content, because everybody gets excited after doing this course. Can I develop a machine by myself? Yes, you can, but with a caution. Okay. Now, let us get into system setup of additive manufacturing machine. So, there are three setups, system setups. One is called as laser powder bed fusion, laser directed energy deposition with blown powder known as laser powder fed. The next one is binder jetting system. These are the most common systems which are used in metal additive manufacturing setups. The laser, when we talk about laser, laser is a coherent source. This coherent source with focused energy can be used for melting. So, what happens is you have energy which is always in joules. Now, this energy, if it is focused on a small area, then the energy densities go very high. So, the advantage of laser is coherent and focused on a small area, which gives you the freedom of melting of powder. So, laser beam which is used always tries to melt the powder. The melting of the powder depends on the selectivity. That means to say, the laser absorbs wavelength lambda. The laser absorbs wavelength lambda, interacts with it and then starts doing it. For example, people use blue laser which has a wavelength close to less than 300 nanometers, generally less than 300 nanometers. So, this interacts very well with copper. If you use a green laser, you might or might not get. When you use a red laser, it will not try to produce a good quality output. So, the laser wavelength is very important and the power is important to melt the powder. The melting of the powder is not like casting, which happens all through. It is done selectively, whatever information you have given in the CAD model. Generally, the laser has two approaches. Laser has projection approach and writing approach. Projection approach means the laser beam is passed through a mask, and the mask information, whatever is there, is trying to get projected on the surface. It can be a metal surface, it can be a polymer surface, but since our focus is more towards metal, we will try to keep metal. So, one layer of mask information is given in the mask. So, now laser is projected through this, it falls on the bed, powder bed where the object is getting built, and all of them melt in one shot. The other way around is we write. Writing is like your pen or pencil writing. So, in your pen or pencil writing, what we do is a stylus is moved on top of a surface. The laser tries to move as spot. These spots try to overlap and they try to form a line, and moment it forms a line, and this line you can try to generate hatch patterns. Through this we try to get a layer formed. So, laser can be used for projection technique, the laser can be used as writing technique. Predominantly in metals we use only writing techniques. So, that means to say the laser scans on top of the powder bed. So, that is what is said here, the laser beam is scanned on the powder layer using appropriate positioning devices. Now, it is very clear. Now, how do I move this spot? You can have laser fixed or the bed fixed. If you keep the bed fixed, the laser moves, right, the laser writes. So, how does a laser write? So, here what happens, the laser from the source is allowed to meet, the laser from the source is allowed to meet a positioning device, or it is trying to hit at a mirror. This mirror will try to focus, this mirror can swivel in XY plane. So, it will sweep and try to take that spot on top of the bed. So, appropriate positioning devices can be used to do it. After the first layer melting is done, the construction platform is lowered and a layer of powder is spread. This gets repeated, so you try to get the final output. So, this is what we have discussed. New powder, we have recoater blade is there or a roller is there. So, it rolls, there will be a heap, this will spread on top of it and you see the model is getting developed. So, this one is called as galvo stage. Galvo stage gives you to write on top of a very large area by just moving the mirror in the XY plane, X and Y plane. mirror in the x and y plane. So, you try to get the final output. Since it is trying to hit at the powder, so a lot of free powder will be there, which will be removed and extracted, used for recycling. So, you see the model here, you see the new powder stock and you see the powder bed stock here. So, when we talk about laser directed energy, in this machine the material is deposited through a nozzle. So, here in this machine you need to have a nozzle. The designing of the nozzle is a challenge. Why? Because through this nozzle you always have a flow rate of metal powder, which is nothing but we can say grams per minute or milligrams per minute, whatever it is, you can try to do it. So, here we should try to have a controlled flow, so that it tries to exactly drop and then you try to melt it. If more amount of flow is there, then improper melting will happen. There will be a melt powder and then a solid powder without melt. So, that is why I said controlled flow rate should be there. So, then this powder will pass through the nozzle and then it will pass coaxially to the laser, then the laser will melt and it will try to deposit, and it is mounted on a multi-axis movement. You can have today a 5-axis robo or a machine to do this operation, nozzle getting fed through 5 axis, you get it, or a table which melts by the laser and electron beam. The material is added and melted layer by layer. The powder is stored in a powder feeder because the flowing in the nozzle has to happen. DED machines, instead of feeding powder, also equipped for feeding metal wires. So, if you want to look at the analogy, you can look at it like a wire arc welding machine. It will be like that only. So, wire arc welding machine is, you have this wire which tries to continuously feed, so that you can start welding a very large area or trying to develop a very good output. So, a metal wire continuously is fed and then it is melts and it tries to grow into 3D object, and the technique is referred as metal or wire arc feed deposition process. Polymers and ceramics also can be fed using this mechanism. So, polymers are also made as wires, and in the same way you can also try to make ceramic, you can also try to have a blend of metal ceramic or metal polymer. You can do all these things to get your output, but by and large here when we talk about it is going to be only wire. So, this is what we were talking about. So, you can see here the laser is coming and the wire is fed. So, this wire, what will happen is you can have a nozzle which is there. So, this instead of powder we can also have wire. It will have a spool. This spool will be connected here. Okay. This is a spool, wire spool, or you can have a metal powder. So, the interesting part is you can have alloy powder or you can have a homogeneous powder, and again in homogeneous you can have varying powder size. Depending upon your requirement, whatever you want, you can try to that. These are all the benefits which metal additive manufacturing gives when the product is developed. So, you try to take a spool, this spool is fed and then through a nozzle, and when it comes here there is a laser which hits here. Predominantly these lasers will be continuous, but continuous if you use, it will always be energy inefficient. So, people have started using pulsed laser, because pulsed laser comes with very high peak energy. So, this can melt and then it can be deposited. So, you can have coaxially 2 nozzles feeding on the side, then the powder coming in the front. So, it gets deposited, you have a XY stage where the stage moves, the laser is constant. In powder bed you can have this galvo where the galvo can sweep, but here the laser is kept constant. This is what I was trying to say, laser can be kept constant, the workpiece can move, or the laser can move and the workpiece is kept constant. Both combinations are useful, and when you keep the laser constant and then try to develop it, you get better output, but again depending upon the process parameters and the condition. So, here instead of the entire setup, you can try to take it to a machine where it is 5 axis. So, today we use 5 axis robos, and these robos are used very well for two things. One, for repair and refurbishment, it is exhaustively used, point number 1. Second thing is, wherever there is a complex job, it is done. Third thing is, today there are even metal bridges which are built in Europe just by metal additive manufacturing through this process. You can do Google and find it out. So, binder jetting we already saw. The binder jetting technique prints complex parts by injecting liquid binder into the metal powder. So, this is how it is. So, this will be the metal powder, this will be the binder plus metal powder. You see the color change. So, it only joins and then it tries to adhere. Moment it adheres, then you have a green part, you try to take the green part to a sintering machine, fire it, remove the polymer, or first wash it and then try to take it for sintering, get the sound part done. So, here it is predominantly, after this it goes for sintering process. So, here it is very simple. You have the liquid container injecting the binder on top of a workpiece. So, the process is explained. Binder is dispensed through a inkjet print head, the similar to laser powder bed fusion. Powder roller spreads the powder, which is then stitched. Okay. The platform is lowered, the next layer is done. The binder jet technique, 3D printing, stainless steel today, polymers and glass is also done today. Again, in polymers you have thermoset polymer, thermoplast polymer, and you have elastomers. So, predominantly these two are done by binder jetting process. Now, let us try to understand this laser, because the laser is the heart. If you understand the heart of the laser, heart of the machine, so then you can try to dictate the process. Today what is happening? New era exotic materials are coming. So, for this you do not have a standard additive manufacturing machine. So, what you do is you try to take powder and then you try to play with the laser parameters to get the best out of it. Okay. So, the important parameters need to be known for AM is little bit of laser theory, laser components, the types of laser. Okay, here types of laser, and then I will try to talk here laser types in terms of wavelength, and then finally the laser beam properties. The laser beam properties are very important, because we always try to say the light hits at a spot and then you try to get, this is only the focal point you say, but laser what happens, you always have something called as a waist. So, anywhere in this area you can keep the object, you get the best performance. This I am trying to draw in terms of, this is Z direction and this may be X direction. So, you have a length, this generally we assume it as a plane, but this is a volume. This might be very very small. So, within this if you keep, the laser gets focused, and while doing metal additive manufacturing you can play with this focusing and defocusing. So, wherever you would like to have an annealing operation, a small heat treatment has to be, you just move either the laser or the bed little bit up and down, you go for defocusing and you get an annealing operation. Once you start focusing, you start getting the sintering process or the melting process. Okay. So, these are some of the fundamentals you should understand, because when you try to use even an existing very good performance metal additive manufacturing machine, once you get the quality output, you should be able to infer where was the problem and how will you sort it out. So, for that also you need to understand the basics of laser. Laser stands for light amplification by stimulated emission of radiation. Planck's law can be derived from the spontaneous and simultaneous emission. Emission is nothing but a process by which an excited atom transition from a lower level by emitting photons electromagnetic radiation. Emission is a process. Here you see emission. It is a process by which an excited atom transitions to a lower level state by emitting photons which are nothing but electromagnetic radiation. The ground state is called as the lower energy orbital, while the excited state is called as the higher one. We will see that in detail in the next slide. When an electron jumps, so this is a lower level, this is a higher level, this is lower, this is higher. You have an atom here, this when you try to hit it with a photon, this gets excited. So, from lower to higher, it cannot stay in the higher for a longer time. So, it will come back to the lower. So, when it is coming back, it is called as emission. So, this is what we described here. Emission is a process by which an excited atom transitions to a lower level state by emitting photons. When it comes down, it has to release energy. So, that is what is called as photons. What are photons? A packet of energy is called as photons. Generally, photons are talked in light related thing, we talk about in terms of photons. So, when an electron jumps to the higher or the lower orbit, the atom emits energy, because if it has to go high, you have to energy can neither be created nor be destroyed, it can only be transformed. So, from here it goes there, from there it comes down. An excited atom emits radiation spontaneously while returning to the ground state. So, when it comes down, when it is decaying, when it is coming down from higher to lower, there is a spontaneous emission. The photon pumping or external heating, the photon pumping, what is pumping? Something has to give the energy, so that it goes from here to here, that is called as photon pumping. I pump energy, right. Photon pumping or external heating raises the energy level of an electron in the ground state to the elevated state, which is E1 to E2. After a few nanoseconds, the electron decays to the ground state while emitting a photon spontaneously. That is why it is called as spontaneous emission. With an energy equivalent to the difference between the two states, h nu is nothing but E2 minus E1. H is the Planck's constant and nu is c by lambda. C is the speed of light and lambda is the wavelength. So, you see there is a relationship of lambda which comes into existence. This lambda is very important, which is nothing but the wavelength. You can always wonder, why do you buy a blue laser? Why do I buy a green laser? When you try to buy an additive manufacturing machine, the vendor says, okay, this machine is wonderful because it has a green laser. What is the big deal of green laser? Is here lambda. This lambda in turn with respect to photon, and this photon is an energy which helps you in melting. So, this lambda is very important. So, if you see Planck's constant, it is always there. So, here we have defined it like this. So, this is what I have explained. So, just one quick recap of it. From E1 it goes to E2. This is what is the pumping happening. So, this is called as the absorption phase. The next one is called as the spontaneous emission. So, from the top it drops down. When it drops down, it tries to give h nu out, that is spontaneous. Stimulated means what hits and what comes out is of the same wavelength. So, that is called as stimulated emission. So, you have illustration of absorption, spontaneous and stimulated emission process. So, E1 or E2 are the energy states. When the incoming photon induces the emission, the process is called as stimulated emission. When the incoming induces the emission, you see this last one, right. When it is induces an emission, the process is called as stimulated emission. In stimulated emission, the emitted photon matches with the stimulated photon phase in terms with phase, frequency and polarization. Polarization means all of them are directed in one direction. When the light comes, you will have, it will go in all directions. It will go in all directions. You will all try to bring in only one direction. So, that is called as polarization. Why? Because this polarization will try to help me in focusing. And when we are talking about metal additive manufacturing and we are talking about roughness of 10 microns. So, grain size of around about 50 microns. The laser focusing spot should be close to this. Okay, then only you can get a good quality output. In a system with many atoms, the process can be repeated, amplifying light and the laser fundamental process. Finally, in a nutshell, the laser beam is coherent, monocolor and collimated. So, this gives you a freedom of focusing. So, the rate equation and the Einstein coefficient, which are always used. So, consider an atomic system with two energy levels E1 and E2. The number of atoms present are N1 and N2 are the atoms or the electrons per unit volume in E1 and E2. The total N is nothing but N1 plus N2, since it is two level system. You can also have 3 level system, 4 level system. When the atomic or the electron system interacts with electromagnetic radiation with a frequency of nu 1 to 2, where h nu 1 to 2 is nothing but E2 minus E1, some atoms will transmit from the ground state level to the excited state level. So, this is the rate equation and the Einstein coefficient we cover here. Einstein assumed that the stimulated absorption rate from level 1 to level 2 is proportional to the radiation energy density, and the number of atoms or electrons in the ground state N1, which is proportional to a constant called B12. So, this is what is the equation wherein which this talks about the absorption rate, where N1T decreases over time. As mentioned, spontaneous and simultaneous emission can cause this atom to decay from E2 to E1. Once it is returning from E2 to E1, it is called as decaying process. It is called as decaying process. Okay. This is called as decaying, and here you can try to find out the absorption rate with respect to time. The spontaneous emission is proportional only to the number of atoms in N2. So, this one we were trying to talk about stimulated absorption rate. Now, we are trying to talk about spontaneous emission rate is proportional only to the number of atoms N2 in the excited state. Therefore, the spontaneous emission rate can be written as A21 N2 with respect to T. So, the stimulated emission rate is proportion to radiation density. Radiation is what comes out, radiation density, and the number of excited ground state atoms N2 with respect to a constant called B21. The subscription order for proportionality constant A and B is 2:1, indicating that spontaneous and simultaneous emission transition starts from excited state 2 to the ground state 1. That is why we call this constant B21. Otherwise, it will be, if you have a 3 level system, it will be B32 and then you will say B21. So, that means to say you are stopping at one level and then you are falling it down to the next level, and from here you are going down. So, here what happens, there is more time, it takes more time to decay from one level to the other level. So, basically when I say this, you will have E3, E2, E2 and E1. From E3 it goes to E2, from E2 it goes to E1. So, here there will be emission, here there will be emission. Okay. So, that is what we are trying to say. You can also have B32, that is why I am very particularly saying that 2:1. So, the stimulated emission rate is given as this equation. So, now the Einstein coefficient B12, A21 and B21 are all Einstein coefficients, which can be directly pulled out from some literature. You can get these constants. Absorption, spontaneous emission and stimulated emission all occur simultaneously when an atomic system interacts with light. All will happen simultaneously. It will not be one after the other after the other. Absorption, spontaneous emission, stimulation emission all occurs simultaneously when an atomic system interacts with light. That is how you get more and more light continuously coming out. The ground state and the excited state population rate equals the sum of absorption, spontaneous emission and stimulated emission. So, that is what minus N1 to T is equal to dN2. So, this is what is the equation. So, now Einstein coefficients are related. In thermal equilibrium, N1 and N2 are equal or constants. So, N1, N2, N2 are this thing. So, we take it as 0. Therefore, at thermal equilibrium, we take the previous equation whatever is given here to become like this, which is equal to 0, and from here we reiterate and we try to get the formula like this. So, what is PV? PV or rho V is nothing but the radiation density. So, radiation energy density per unit frequency interval, and according to Planck's law it is given by this. So, this is the radiation energy density, and according to Planck's law it is given by this. So, sigma B is nothing but this is the Boltzmann constant and T is the thermal equilibrium temperature. The number of atoms or molecules in the jth state with energy GeJi at a thermal equilibrium is given like this, where C is a proportionality constant. So, considering the ratio of population level 1 to 1 and 2 at thermal equilibrium temperature T, it is given by N2 by N1, which is e to the power E2 minus E1 negative sign divided by sigma B by this. So, when you realter this with the previous equation, you get the energy density is nothing but rho V is reiterating. Just by reiterating, you are trying to get N2 by N1, you try to go back and then you see Nj. So, rho V, from here you try to bring to this equation and try to get the output. So, now we compare 7 and 7 this equation with respect to 11, and then we try to get B12 equal to B21. This result show that absorption and stimulated emission process are equivalent. So, then we get to know more about A21, and A21 is nothing but E rho h nu cube 1 2. So, this is energy. So, this is Planck's constant whatever we are talking about, B21 C star 31. So, you see all the proportions we have discussed in the previous slides, asserting the absorption and spontaneous emission are proportional to each other. So, I was talking to you about 2-level system and 3-level system. In 2-level system, for stimulated emission to produce a laser beam or amplifying light, the stimulated emission rate must be higher than the spontaneous emission. Stimulated emission and spontaneous emission. Please try to understand this, because this will try to distinguish between this. Many a times we try to interchange stimulated emission and spontaneous emission. So, let us go back and see what is stimulated emission and what is this is stimulated and spontaneous. Spontaneous means instantaneously what is released is called as spontaneous emission. Stimulated emission means you are stimulating, you are getting the base back plus one more energy which you are getting, that is stimulated. So, this is what we are trying to cover here. We are trying to talk about stimulated emission. So, the stimulated emission to produce a laser beam or amplify light or stimulated emission rate must be higher than the spontaneous emission and absorption. This can be expressed by the following equation: B21 rho V, which is the frequency given, N2 should be greater than this B12. So, now B12 and B21 we are giving it here. So, B21 in equation 12 you can see that they are constant. So, we are taking it from there and putting it in equation 14, we now holds N2 is greater than N1, meaning more atoms are in the excited state than the ground state. This is called as population inversion. More amount of atoms are there, number N2 is there as compared to that of N1. So, 2 level system and 3 level system, 2 level is E1, E2, 3 level system will be E1, E2, E3. So, here spontaneously it falls down. So, here it goes up, goes down here, one emission will come, from here it will come, so 2 an emission. So, here your efficiency goes high, this is 2 level and this is 3 level. Nowadays, you also have 4 level systems. How do they do it? They try to do doping of the glass, or they try to have optical fiber is doped, they add materials, ingredients. So, now laser efficiency has gone up very high. Population inversion, so this is what is called as N2 is greater than N1, so that is called as population inversion. Population inversion causes this. According to equation 10, at thermal equilibrium, the population density related between level 2 and 1 is given by Boltzmann distribution. See, I have now covered so many things. Slowly if you walk through, I have covered, first I talked about Planck's law, right. Then I talked about Boltzmann constant, then Planck's constant and Einstein. So, now we are trying to see Boltzmann. So, almost all these constants and distributions are all getting integrated into one thing called as laser. People who do this course, I want them to understand little bit of these basics, because this will try to give you a better understanding what is happening. Even today, the continuous lasers have an efficiency of 20%. Why 20? Why cannot it go for 80? It has a thermal management system. So, what stops them? Can I shrink the size of the metal additive manufacturing? What puts the stoppage? If you understand this, then you can understand that nicely. That is why I am taking pains in going through all these things. Distribution N2 must be lower than N1. So, N2 is less than N1. So, the thermal equilibrium, population inversion cannot occur. So, the rate of equation for this type of system is given as this. So, this is a 2 level system. So, hence since B12 and B21 are equal, we omit the subscription of for the Einstein coefficient B, and since the spontaneous emission takes place only from level 2 to 1, we can omit the subscript 1 to 2 or 2 to 1. That is why we write it as B a constant. So, 1, this is 2 level system. At t equal to 0 time 0, all the atoms in the ground state 1 or N1 is equal to N2 total and N2 is equal to 0. Rewriting equation 15, so N2 is this. Now, if we rewrite this into this, this is what is the final equation we will get for N2 and N1 for 2 level system. Since A is greater than 0, so equation 17 for a given value of t, we can write it as this. So, you can see N2 is nothing but N1 plus N2, which is less than half. At thermal equilibrium, the number of excited atoms or the electrons will not exceed the number in the ground state. So, population inversion cannot happen. So, population inversion is a term which we generally use it very liberal, but there also there is lot of science behind it. I am just trying to bring all those things to your knowledge. So, as I told you, there are 3 level systems also. So, from E1 it goes to E2. So, when it gets excited, it moves from E1 to E3 direct. So, E1 to E3, now you see B31 comes into existence, right. So, from here to here it goes, and then from here to here it comes, it is the B31, right. So, generally what happens, from E1 to E2 it goes, from E to E3 it tries to fall at a level called E2 and stay there for some time. So, then you have a A32, B32, A31 and A21, all these things are there. Okay. So, B31, A31, A21, A32, B32. So, now you see there are 3 level systems. So, the efficiency of the process goes high. So, whenever it comes to here you will emit 1 photon, from here you will emit 1 photon. So, earlier it was only 1 photon all throughout, now you have 2 photons or 3 photons coming out. So, the spontaneous system the 3 level system with a level 1 representing the ground level and the level 2 and 3 representing the excited state with energies E2 and E3 respectively. In a 3 level system, population inversion is possible. This system will lace when N3 is greater than N2 due to the population inversion between the excited state 2 and 3. So, here Bij is equal to Bj1, B indicates absorption and stimulated emission between 2 states. Before atoms interact with radiation, N10 is equal to N total. When the system interacts with electromagnetic radiation with radiation energy density rho v, here Hv is nothing but E3 minus E1. Some atom transition from ground state to the excited state. Pumping source radiation exits the ground state. So, now the total is going to be N1 plus N2 plus N3. The atom is in excited state 3 can relax by stimulation of spontaneous emission to level 1 or 2. The total amount of 3 level system equals the number of energy levels therefore. So, you can see more and more levels you have, more and more emissions you will have. So, this is what is have. So, they say when you buy a laser it is 2 level laser, 3 level laser, sometimes they do not even tell you, and once you know this you can see why, because this in turn directly tries to hit your m square value. What is m square? M square tries to talk about the accuracy of your laser. So, for m square value indirectly these levels also come into action. Of course, for energy it has a direct influence, but m square also it has. Similar to the 2 level system, the rate of emission can be written and solved for each of the population state 1, 2 and 3 due to pumping. Each level population is constant at equilibrium. So, you can take dN1, dN2, dN3. So, 3 levels. So, the second rate equation, the population N2 is given by the spontaneous emission from state 3 to 2 and state 2 to 1. So, the stimulated emission from 3 to 2 and absorption from 2 to 3. So, the state 2 rate equation when equilibrium is maintained will be like this, and you will get 2 equations by rewriting it N3. So, N3 will be rewritten like this. So, faster than the atoms in state 3 decay to state 2. So, from here to here, here to here. So, atoms in the state 2 decays to state 1 faster than the atoms decay from state 3 to state 2. From here to here more time, from here to here less time. So, more and more time, more and more emission can happen. 3 level systems are more than 2 level systems gain medium. So, you have also 4 level as I told you. So, from here it gets excited to this level, from here it goes non-radiation fast decay happens up to 3. So, from here it goes to lasing action happens here, from here to here it goes down. So, you can see pumping action and lasing action, it goes to this level. So, here non-radiative fast decay will happen, from here to here it will be there. So, if you see that, so it will try to be more efficient when we use a 4 level system. So, the ground level has an energy equivalent to E1 and is indicated by 1. The levels 2, 3 and 4 are excited states and their energy levels are 2, 3 and 4 respectively. When level 1 atoms are excited to level 4, they relax to level 3 and a metastable level with a longer lifetime. So, that means to say it has a longer lifetime, then from 3 to 2 it causes lasing action and then it tries to come down. So, to maintain lasing, level 2 lifetime must be shorter. So, atoms can quickly relax to the ground state and go back to the level 4. Level 2 must be above level 1 and unpopulated at normal temperature, which is sometime accomplished by lowering the system temperature. So, this is where we use heat management as a tool. When we try to look at the lasing components, main components of the lasing system are gain medium, pumping source and optical resonance. Optical resonance are nothing but, so where there is a back and forth movement going on. Gain medium means where you try to focus and gain things. Pumping source means what tries to excite the ground level. So, you see generally what will happen is a laser cavity. By the way, these are all for schematic explanations. Today we have optical fiber which is used as a lasing gain media and it tries to produce an output. So, things are changing in a very big way. So, fiber lasers are also available today. But just for your understanding, we will see the schematic diagram so that you know the ingredients whatever it is. So, optical fibers are very small, very small. So, through this also today they are trying to do. So, here they have gratings and this gratings helps for multiple reflections. Let us keep moving here. So, laser cavity. Laser cavity means it is assume that it is a closed cavity. It is like a box. So, at one end of the box is totally reflection and the other end of the box is partially reflection. Total reflection means, so it is 100%, partial reflection means it is 95% to 98%. So, here what happens is you will have a medium. So, in this medium you will have all the atoms at the ground level. When the pumping source hits it, the pumping source can be two. It can be a laser itself, can be a pumping source, or you use a IR or any other light source, you can use. You can use laser also. When you use a laser, whatever comes out, you will have two wavelengths. Very clearly you will have two wavelengths. One can be, say for example blue, the other one can be red. And then what will happen is you put a filter for red and you try to get only blue out. It will be very distinctly seen. Okay, you put a filter in between and cut it off. The beauty of laser is you can try to put lenses and you can try to chop off. Whatever you do not want, you try to chop off. So, that is the best part of this laser. Okay. So, you have a gain media. Gain media is a place where all the electrons are in ground state. So, pumping source is hit. So, it moves from E1 to E2 or E3, E4. So, now it is getting excited. Moment it is releasing, it release the photons in all directions. Now, this all directions they are moved back and forth, back and forth, back and forth, and once it reaches a level of 98% of all of them in one wavelength, then there is a out through which, or this is an out through which the laser light comes out. So, the basic components of laser system is gain medium, that is where you have E1, E2 and other things what we read till now, pumping source which tries to excite from E1 to E2, and resonance to maintain and get all in one particular direction. So, the active media or the gain media and mirrors that reflect emitted radiation from the cavity system. To excite the gain medium atoms or molecules, a pump is used. So, this is what I have explained to you. So, all these things are there. So, all these things are now shrunk and then they are put into fiber optic. So, you have fiber optic laser is also available, and depending upon the power, see these systems can be used for very high powers, continuous very high power laser. This is how is the schematic. When you want to have a pulsating very high power, but a continuous power of very low joules, then they go for fiber optic cables. Gain medium, or also known as active laser medium, is made of atoms, ions, molecules or electrons. Depending on the gain medium, the laser can be have different wavelengths. So, this is what. So, you can have a semiconductor laser, you can have a gas laser, you can have a liquid dye laser. All these things are now the gain media. Depending upon the gain media, you can try to have different wavelengths. You can have solid, liquid, gas, dye or semiconductor as a media. Gases, you have gaseous lasers also. So, for example, CO2 is a gaseous laser, excimer laser, okay. All these things are there. The first laser was a solid ruby laser alumina with chromium ion replacing aluminum ions. Lasing ions can achieve population inversion in alumina due to their electronic energy levels. So, the first laser was the solid ruby, alumina was used with chromium ion replacing the Al3 ions. E1 to E3, E1 to E2 you can go. Pumping source. The pumping source excites gaining medium atoms from a ground state to a upper excited state, creating population inversion necessary for lasing action. The lasing media can be optical or electrically excited. You can use a very high power, and then also you can do like an arc. So, you can use very high power and then you attach it very high power. So, it creates an arc. Okay. So, that is what electrically excited also can have, or semiconductor is an electrical excitement. First, the active laser media is excited by a higher intensity light source such as a flash lamp and a laser or a laser. The lasing media excitation by an intense electrical discharge is known as electrically excitation approach, the gas pumping this way. So, what we are trying to say is you will try to have arcs or a capacitor, bank of capacitor you will have. So, in this bank of capacitors you will try to pass very high current. These are all capacitors. So, when you pass very high current, it creates a spark. Now, you try to pump in gas, and what comes out is a laser which is excited. This gas, it all gets by the arc, it all gets energized, it tries to create a plasma, and then that is further moved, and then you have multiple mirrors, then you get an out that finally comes out as a laser. The laser medium excitation by an intense electrical discharge, this is what I said capacitor, is known as electrical excitation approach, and the gas is moved through it. You can have solid or you can have gaseous laser also. Once the population inversion in the gain media is reached, the light intensity is amplified by forcing stimulated photons back and forth across. That is why I told you there is a medium. So, this is fully reflecting, this is partially reflecting, this is fully reflecting mirror, this is partially reflecting mirror. So, it amplifies inversion in the gain media reaches, the light intensity is amplified by forcing back and forth movement of photons. The laser media is placed in a resonating cavity to amplify the light. The length of the resonating cavity is important, which will try to dictate the amplification. The cavity has two parallel mirrors, direct light through the laser medium back and forth. So, one side is 100%, the other side is less than 100% to get the required output. When we go to the next understanding of laser, level of understanding of laser is we should try to understand what is continuous laser and what is pulsating laser. So, the continuous laser versus pulsating laser, laser are categorized as continuous and pulsating. Continuous means it is like this. So, power with respect to time. So, you have a constant power coming up. This constant power, if you have a very high energy, then you can use it for sintering high energy, then you use it for sintering and melting or melting, but this is continuous. When we have a same laser, but now what we do is we chop it off and we try to have the same energy here into a large energy, we have a huge energy. Okay, I will redraw it. So, the same thing, if I try to chop it, same laser power, what do? I try to segment it and then I try to chop it. So, and then chop it and release it as instant. So, I have a very high power for a very short duration. Same thing, I compress and I release, same energy. So, the peak power will be very high, but the average power for this also will be the same. So, this is where you get a very high peak power to melt. So, always we prefer to use a pulsating wavelength laser. Continuous is also there. Continuous is not so very energy efficient, pulsating is energy efficient, and here since it is only a small packet of energy of very high thing comes. So, the circuit also need not be so robust like that of continuous. and continuous after a certain peak power if you want to go, it becomes very inefficient. Today the continuous laser we are talking about efficiency somewhere close to 15 to 20%. So, if you apply 1 kilowatt of energy, you can get only 200 watts of energy which is useful, which comes out of the laser, which will then get into the system and then you do. So, finally the efficiency will boil down to 3 to 4% only. Okay. So, that is why people are now using pulsating laser. The first generation laser produced a continuous beam whose characteristics are determined by the gain media. What is the gain media? The material which is kept there. The continuous laser was helium neon laser which 1153 wavelength, nanometer wavelength. Since then, gaseous laser, solid state laser, dye laser has been developed. The different types of pulsed wave lasers are also available today depending upon the pulse duration. What is pulse duration? This is duration, and then energy, this is energy, repetition rate, this is repetition rate 1, 2, 3, and wavelength. So, you can try to have. So, different types of pulsed wave lasers are available today in the market, where it depends on pulse duration. This is what it is. It will be in millisecond. Okay, let me write down the durations. Duration, it can be in nanosecond, millisecond, microsecond, it can be in picosecond, or it can be in femtosecond. All these things are the pulse duration we are talking about. Energies, it can be in kilowatts. Repetition rate, again it can be from 10 hertz, it can go up to kilohertz. When you go up to kilohertz, the power will go down. When you have a lesser repetition rate, you will have a higher pulse energy. Wavelength is also there. Q switching and mode locking generates nanoseconds and femtosecond laser. These are mode lockings which tries to chop whatever I said here. Q switching and mode locking. So, Q switching and mode locking are other interesting concepts which we will see in the later part of the course, and that helps you to chop. So, till now we have seen little bit fundamentals about laser. So, we saw what is laser, what are the different types of laser, 2 level, 3 level, 4 level, what are all the basic construction of a laser, then what are the two different types of laser, continuous and pulsating. We will continue in the next lecture to understand more on the laser parameters. Thank you very much.